But that's my microphone.
I mean, so since Gather is running on this laptop, which is why.
I didn't. I thought I had this. Okay, so we find the state parameter that goes failure. And what we want to do is we want to compute hyperparameter values that distinguish the failures. So there might be this something that says that all the failures will have this in common and none of this in common. So this is the thing that's causing problems. And this problem actually can be expressed with symbolic execution. So why symbolic execution? One answer is, well, I like symbolic execution and I like control my music. But there's another reason actually, which I want to get to next. But before that, I need a little bit of background, which is a little trial. So a trial, when I'm using the term trial, is one run of a pipeline. So we're doing a search for different pipelines. We're trying different experiments, and each trial is one concrete configuration of the pipeline and the hyperparameters combined with an outcome. So we say an outcome is true if it had no error. This is not how well did the pipeline do in machine learning. This is something much simpler. Did it crash? Rather, it failed somehow. And it's true if it had no error. If the outcome is true, it had no errors. If the outcome is false, it didn't produce a bad answer, it produced no answer at all. And then value TP is the value of each, the hyperparameter P in trial T. So each trial will have, for example, if one of the trials includes a computer, it might have set the strategy to mean or something like that. And that would be the value of, in trial T, of the hyperparameter simple imputer dot strategy. So given that background, let's see what we do next. Let's look at our symbolic algorithm. So if we only knew, if we already knew the answer, we knew which hyperparameter and which value is bad, it'd be very easy. Right? We say that P is some hyperparameter, op is some comparison operation, and V is some values. Notice I'm just undifferent, just some. Don't think too carefully what they are right now. And what we do is for each trial, we want to assume that the outcome of T, outcome of the trial, is equal to the value of the hyperparameter P of V, which basically says that this is we're going to read this hyperparameter from each trial, and if that test is true, the trial succeeded. If that test is false, the trial failed. And what that would do, if we can figure that out, that would mean the assertions mean that P of V determines the trial outcome. It means we found the right hyperparameter, the right operator, the comparison of subset, and the right value, a number, a string, whatever it is, that indicates whether that controls whether or not the trial succeeds. That is, doesn't crash. Now, then right at the top I have this word solve, we're doing something symbolic. So what really is going on is these are going to be symbolic values. There is something that a solver has to fill in to figure out what's going on. That's what solve does. And if it's possible, solve binds P, op, and V to something that controls whether or not the trial succeeds. Please do interrupt me if things don't make sense. So that's basically what's going on. Now, one thing we add in Maro is that's when there's a simple value. Like this comparison is there's a single value here. It's like, strategy, simple individual strategy equals mean, or something like that. But one kind of thing that's a little bit more complicated is when you have two hyperparameters that are related. For example, imagine if you're doing something with with polynomial features or something like that. You can have limit how you can have something that creates features, and then you can have something that removes features. Obviously, if you can't create fewer things than you end up needing. So these hyperparameters can be related, and so we've made this a little more complicated, which basically says that it's the same assertion before outcome T is now equal to either the value, which is the same thing as before if it's value, or it's the value of some other hyperparameter in the trial. So it could be that when I create, some number of features, and then I want to choose K back. So let's say I have something in compute these polynomial features, create new features, and then I want k best. I want the best 10 features. Well, what if I only created 5 features and then I wanted the best 10? That's not going to work. Clearly, I need to have at least as many features as I want to choose. So that's the kind of place where you'd have this. It would be if the parameter kbest dot k, I think, is greater than polynomial features dot n, something like that. I need to keep doing that. But this is basically the question. This is basically what we're doing. And one thing to look is the thing with symbolic, the way to think about symbolic execution is this would make, if we knew what we were putting, if we knew what these were supposed to be, this would be a trivial piece of code. This would just be checking that the answer is correct. And so symbolic execution is basically taking that and turning it into a search function. So how did we implement this? We implemented it in our solve-rated virtual machine called Rosette, and basically what it does is it extends racket scheme with symbolic variables. And running, since we have these symbolic variables, running the program, it doesn't produce an answer, usually. It produces an SMT problem to solve for appropriate values for all the symbolic variables. And it turns out we can implement the story sketched from the slide, we can implement pretty directly with Rosette, although there are a couple of issues. One is some comparison operator. Now, you one might think, well, I'm just going to ask you to come up with a piece of code. That's not even finite, and certainly not possible in any reasonable way. So what it actually is a choice from a set, which includes less than, greater than, equal, stuff like that. Things that basic operations, essentially. So it's not an arbitrary, unbounded set of functions. It doesn't have to invent code. That would not generally be possible, make sense. And value, I just said, think of just some random value. In Rosette, it's actually, they're split by type. Because you can't, again, if you're trying to invent a value, it has to, the way Rosette works is it has to invent something of the correct type. That's the way it's on, that's how it's driven. So we support booleans, numbers, and strings, and those are the types of value we have. There are actually 3 different cases. Now, I'm going to do something that's not usually a good idea. Perhaps it won't be a good idea this time, but let's see. I want to actually show you some code. This is literally the code in C and Racket that's driving some different steps. So the first thing we need to do is, I don't know what that is, but anyway, this is doing OK out the third run. So this is third run just turned out to be the list of all the hyperparameters in the current trial, all the hyperparameters and their values. So we're going to look through all of this. Now, the first question is we're going to say, is this the right hyperparameter? So hyperparameter is coming into our search. It's parameter. Is this the hyperparameter that we are looking for? And so we say first of all, this is the first pair of parameter comma value. This is the first parameter, and we're just checking whether it's equal to the one. So if that were concrete, it would simply be checking whether this is the hyperparameter we were looking for. Because it's symbolic, this is actually saying we're going to create a problem and solve it. And then if it is, now let's see. What is it? Stop it. Yeah, this is we're going to take this. And if it's now, that's the question is V, that's the value for this is concrete again, sort of the value, but this is a number. If it is, we're going to check the comparison with whatever the numerical. And again, this is the symbolic value. This is going to find is the thing in the data actually equal to the symbolic constant. And we can skip this one for time. Now, remediation, we get failures, we find the step, we shift hyperparameters. And the other thing it can also do is we have this notion of explanation that say things like take the argument strategy and make it less frequent. Compared to existing work, this symbolic approach is successful. We took 20 problems that are in our paper, we ran them on this, and the most recent work was this system called Shortcut, and we solved substantially more of them. And Thank you.
Okay, maybe we can take questions while the last speaker is setting up. So, questions? Maybe okay, go for it.
Thanks for the talk. Can you say something about the set of AutoML tasks that you think this kind of method could be good for? What types of data pipelines do you think that this could satisfy?
You mean data for the hyperparameters?
So you mentioned figuring out how to handle missing variables as a type of situation where this could be useful. What other situations? Like what's the kind of more broader kind of set of situations?
Well, basically, the way the symbolic evaluation is working is essentially any time you have a hyperparameter that causes failures, it's a very, we don't understand anything about what any of these operations do. It's simply looking at what things fail. So one common example is when I was talking about polynomial features and select k best, for example. I make a bunch of features and then I choose the best one. We figure out that, well, you have to make at least as many as you want to select. You want the best 10 out of 5. That causes the system to blow up. And that's the kind of thing, that was sort of the motivation actually for the second case, I was saying compared to hyperparameters. Other examples are things like mean. A lot of the time people will try to try mean, but that only works obviously on numeric data. It's also most frequent, it's more general. Then you have select k-best, if you select k-best, you have to have at least that many. If you put that in your pipeline and you wanted more features than you had columns, that also would work. Those are the kind of things, but what it does is it finds, those will cause pipeline failures, but it will not, and what we will tell you is you will need to make it this big. It's not there's no sort of philosophical reasoning about, well, you didn't have enough columns, so it will say that k-best had a number that was too big to use.
So following up on that question, do you expect the constraint-based approach to scale to, the sort of AutoML tasks that people are solving in the industry?
So the way it works now is we have two kinds of things going on. One is how many trials you have. Because we basically, you could see, we did for each trial, so we're constructing it that, and then also how complex your pipeline is. And then so far, even when we use those quite a few trials, so far the solving time has been negligible by and large. We're using Z3.
But it's going to grow exponentially, right?
Clearly, it will break eventually. I mean, yeah, if it's running, just make it bigger, and if it keeps running, make it bigger again. It's got to stop eventually. Now, on the other hand, a lot of the things that are going on though, when it's reasoning about, like, for example, whether a parameter has to be less than 3 or something like that, the system is pretty good at recognizing that, it's pretty good at reasoning about numbers. And the other thing is, I said we support strings, and that's true, but hyperparameters, when they take string values, they're really mostly categoricals. So the only thing it's really dependent on is the ability to do string equality. And that's easy, right? It doesn't actually, you could reduce it to numbers if you wanted to. Hyperparameters you don't usually have a crash that says, well, if my hyperparameter string starts with A, B, C, or D, but not any letter beyond that, that you don't tend to see that. So we're looking at relatively simple operations, and it's been fine so far, but you're clearly right that eventually something will have to blow up.
Okay, thank you.